Let us talk about this problem. We are given a singly linked list and we need to pairwise swap nodes of the linked list. For example, if the linked list is 1, 2, 3, 4, we need to change it to 2, 1. These two are swapped with each other. Then these two are swapped with each other, 4, 3. If you have odd nodes in the linked list, then you need to simply ignore the last node. So you need to change it to 2, 1, then 4, 3, then you need to leave 5. If you have a single node, then it's again an example of odd nodes. You need to simply return the linked list as it is. If you have an empty linked list, right, null or none, in that case also you need to simply return empty linked list only. Now please pause this video and try to write down a function that takes head of a singly linked list as argument and returns head of the modified linked list. Let us first talk about a naive solution to solve the problem. The idea is simple. We traverse the linked list starting from the beginning. We mark current as head, and we run while there is one node ahead of this node. And inside this loop, what we do, we swap current's data with the next node's data. So we come here and we swap these two data, right? We swap this data, this node's data with this node's data. So this becomes 2 and this becomes 1. And after swapping this, current was initially here. We move current 2 nodes ahead. So we make current equal to current dot next, right? So now current comes here, we swap the data of these two as well. So we swap 4 and 3, right? We do it in a loop. Key current begins from head, swap current node's data with the next node's data and move current 2 nodes ahead. And after that, move it 2 nodes ahead. Now there is no node ahead of it. We are running this loop while there is at least one node ahead of the current node. So we come out of this loop at this point and we modify the linked list. So this is the simple idea. And why am I calling it naive method? See, this solution clearly requires theta n time, right? Simple solution. But it's called naive method because we are swapping the data and your linked list might not be containing simple integers. It might be containing, some data objects of large data like students data or some large objects or teacher object or a subject object, right? Which might be having many fields. And swapping the data would not be a good idea in those cases, right? And typically we have data structures of objects. So in those cases, it would be inefficient. And if you have single integer data, then the solution is fine, but not a recommended solution. The better solution would be by changing the links here, right? We change the links, we don't touch the data, right? We change the links. So first, please pause this video and write down the implementation of this naive method. Then we'll talk about method of changing the links. Here is implementation of the naive method. We have a function pairwise swap that takes head of the linked list as argument. It begins with current equal to head and it runs while current is not equal to null and current arrow next is not equal to null. See, this condition will be false. We will come out of this loop because of this condition being false in case of even nodes. And in case of odd nodes, you will come out of this condition because you will come out of the loop because of this condition. Now, what are we doing inside this loop? We are swapping current data with current desk data and we are moving current to current arrow next. So if you have this linked list, what you're going to do, you are going to first swap these two data in the first iteration. You will swap 1 or 2 and then you will do current equal to current next. So your current will come here, right? This is what will happen after the first iteration. And in the second iteration, you will again swap current data with current next data. So you will get 4, 3 and then you will move current to current next. So current comes here. Now this condition becomes false and you come out of the loop, right? So you will have 2 iterations and your linked list will be modified. And please note that head of the linked list is never changed this implementation because we are swapping the data, right? Although return head, you can write the void function as well. That will also work. So what is the time complexity of the solution? This is clearly theta n and it requires theta 1 auxiliary space. But the problem with the solution is if your linked list is of large objects, then it's going to be inefficient. So a better general purpose solution would be to change links. Now please pause this video and try to write down a solution that change links of the linked list rather than swapping the data. Let's now talk about idea for the efficient solution. You must have guessed this much that we are going to run a loop and inside the loop we are going to change the links. So say you are given this linked list, you have this first node and then you have these 5 nodes in the middle, then you have this last node, right? I use dots here and say this is some middle linked list and then this is last node. Now when you are traversing through a loop and you need to change the links pairwise, when you come at ith node, you must have processed these nodes. So when I say process these nodes, what it means is xi minus 1 must have moved here and next of xi minus 1 must have moved as xi minus 2, right? These two must have been swapped their position by changing the links. And when you come to xi, you need to fix these two nodes, right? And you need to make this node as previous, xi as this, before your next iteration begins, right? So in the current iteration, you need to change these two in such a way that you are ready for the next iteration. That xi plus 1 comes here, xi comes here, and it becomes previous, and xi plus 2 becomes current, right? That's all you need to change. Now please pause this video and try to think of the things that you will write inside the loop. So you will basically run a loop while current is not equal to none or null, and current dot next or current arrow next is not equal to null or none, right? And inside this loop, you will write some statements. And what statements to write, you can guess from this diagram, right? You can take a closer look at this diagram and you can guess the statements that you are going to write. So to give you more hint about the statements, what all you need to do is, you need to make this previous is next as currents next. Whatever is the currents next should become the previous is next, right? And the current should become previous, right? And this should become current. These are the changes we want to make. And are there any more changes? Yeah, its next should become this. Its xi plus 1's next is currently xi plus 2. Its next should be changed to xi. This is also one change. Xi plus 1's next should be xi. So these are the changes we need to make. Now please pause this video, try to write down the logic, take a closer look at the diagram that you need to write to finish this work inside the loop. Here is implementation of the idea. Let's first take a look at this loop, right? And then we'll talk about remaining code. So for this loop, this is our input. We have processed nodes from first node to xi minus 1. They got swapped, right? This was our initial list, they got swapped. And currently in the loop, we are say at this node xi. What we want is, we want this loop to modify this linked list to this linked list, right? After this loop, previous should be here, current should be here. This xi plus 1 must have gone between these two, right? And xi plus 1's next should have been changed from xi plus 1 to 2. So initially it was xi plus 2. It must have been changed from xi plus 2 to xi, right? That's the change we want in the linked list. So how does this loop make this change? It's the simple step-by-step process. We are just changing links here and there. So previous is next becomes current's next. So let's see what does this step do. So previous is next becomes current next. So its next becomes this. This is what current next is. Then what we say, we may say previous is equal to current. So we move previous from here to current. Previous now comes here. That's what we want in the output. And after that, what we are doing. See, before I talk about these three lines, let's take a closer look at this diagram and see what we exactly want to do after these steps. So what we want to do now is, we want to change next of this from here to this node, right? Xi plus 1's next should become xi. And we want to update current as this, right? So if I simply change current arrow next as current, that would be a problem, because if I simply change the next, I'll lose the hold of remaining linked list. So what I do for avoiding this problem, we first get hold of the remaining linked list in a variable called next. We get hold of the remaining linked list in current arrow next in a variable next. And then what we do is, then we make the required change. Current arrow next becomes current. So what this does, it changes this next from here to here, right? It changes to here, right? That's what we want, right? In this diagram. Now, after that, we change current to next. So current comes here, current is moved from here to here, current is now here. And that's what we want. If you take a look at this diagram, we have got the required result. Let's now quickly talk about this line. So after the loop, what happens is, if you have even number of nodes, then your previous would be at the last node, right? So if you have, say, 2 or 4 nodes, right? Say if you have 4 nodes, then previous will be at the last node once you have finished. And what will be your current? Current will be null, right? It will be null after you process everything. So what you want to do is, you want to make sure that previous is next is null, right? It's going to be your last node after everything is processed. So previous arrow next is made as current, right? That makes sure that in case of even nodes, you have null. Now if you have odd nodes, then your previous is here and current is here. and this is the last node, and what will happen, your loop came out because of, you came out of the loop because of this condition, current is here. Now what you want to connect these two. So again, in this case also you want to make previous arrow next as current. So in both the cases, this line works. Let's now talk about the lines before the loop. So here we are handling the case explicitly when our linked list is empty or when the linked list has single node. In that case, we simply return head. The linked list does not change. Now, why are we handling the first two nodes explicitly? See what happens in case of first two nodes, our head pointer must be changed, right? So say if you have this linked list 10, 20, 30 and then you have more nodes. So what you want to do is you want to change the head pointer to here, right? And this happens only in case of first node, first pair. You want the head to change to 20. For that reason, I have handled the case for first two nodes separately, right? And this code is actually doing something similar to this only, right? What we are doing, we are changing current equal to head arrow next, so current comes here. Now we are making previous as head. So previous comes to this node 10, right? That's what we want. Then what we are doing, head equal to head arrow next. So head is moved to 20, that's what we want. And we are making head arrow next as previous. So we are breaking this link and we are changing this to 10. That's what we want, right? So first two nodes are handled explicitly, and after that the loop handles the same way remaining nodes. So this is how this code works. The time complexity is clearly theta n and auxiliary space is clearly constant.